Okay, today we're looking at Cartesian and parametric equations. Starting with this example over to the right here with the line AB with undetermined coordinates, so they're just pronumerals at this time, and we're asked to find the distance between the 2 points. So treating this as a vector, it's going to be the difference of the coordinates, the squares of the differences of the coordinates under the square root. So distance is equal to square root of x2 take x1 squared plus y2 take y1 squared plus z2 take z1 squared. The midpoint of the line, so let's call it MAB, is going to be found by just taking the average of the coordinates of this. So MAB is equal to x1 plus x2 on 2, y1 plus y2 on 2, and then z1 plus z2 on 2. So a sphere with radius r and center C xyz has Cartesian equation r squared equals x take xc squared plus y take yc squared plus z take zc squared. We've already seen the Cartesian equation of a circle, so to turn that into the Cartesian equation of a sphere, we're just adding on that z component there. So let's apply this to example 10. Determine the Cartesian equation for a sphere that has points A and B as the endpoints of its diameter. So thinking about what we need to know for a sphere, we need to know its radius and we need to know its center. So how are we going to get those 2 points? Well, let's start with the center. The center is the midpoint of the diameter. So to find the midpoint of the diameter, that's going to be C is equal to 6 plus negative 2, which is 6 minus 2 on 2. It's going to be 12 plus 4 on 2. And it's going to be 11 plus negative 1, which is minus 1 on 2. So the center that we get is 2, 8, and 5. The next point we want to know is the radius. So the radius, just like we looked at earlier, is going to be half the distance between A and B. So half of D, which is equal to half square root of the differences of the components. So let's take A away from B because A are all positive, so it's going to make it a little bit easier. So 6 take negative 2 is plus 2, plus 12 take 4 squared, plus 11 take negative 1, which is plus squared. And so what we get here is that is, let me just check my notes. The radius is square root of 68. Right, so that's after applying the half there. So that means that our r squared value is going to be 68. So our equation is 68 is equal to x take 2 squared plus y take 8 squared plus z take 5 squared. And all those points just come from our center up here. Okay, part B is asking us to determine the center and radius of the sphere with the Cartesian plane x squared plus y squared plus z squared minus 12x plus 4y plus 8z plus 20 equals 0. A little bit of a mouthful there. So to start with this, we want to complete the square for each of those components. So we're completing the squares. So to start, we want to rearrange them so that all of our common components are together. So x squared minus 12x plus y squared plus 4y plus z squared plus 8z and then that's equal to negative 20. I'm going to take the 20 to the other side. So looking at these three terms here, negative 12x, 4y, and 8z, they're the b term that we have to half to complete the square. So if I'm going to add to both sides, x squared minus 12x, half of 12 is negative 6, squared is plus 36. If I'm adding that to the left, I also have to add it to the right. Okay, the second term is going to be y squared plus 4y, half of that is 2, so that's going to be add 4. We also have to add it to the right. And then the last term, I'm just going to draw it down here, is z squared plus 8z plus half of that is 4, so that's going to be 16. And we have to add 16 to the right. So what that allows us to do is we can now factorize these as perfect squares. So we get x take 6 squared plus y plus 2 squared plus z plus 4 squared. And that is going to be equal to 36. So we can see here that we have center of 6, negative 2, negative 4, and a radius of the square root of 36, which is going to be 6 units. All right, and that's our answer for B. Moving on, looking at parametric equations in 2 dimensions. So a function defines a dependent variable y in terms of an independent variable x. So consider the Cartesian equation y equals negative 0.01 x take 10 cubed plus 7. The function models the position of a particle traveling along a water slide. It would also be useful to know when the particle reaches a certain point. This is achieved by introducing time as a third variable called the parameter. If it takes one time unit to travel every one horizontal unit, i.e. x equals t, then the parametric equation defines the location of the particle in terms of time, which would be y equals negative 0.01 t take 10 cubed plus 7. Not sure where my minus went there. Note, any letter can be used to represent the parameter. While t is commonly used, it does not have to be defined as time. Theta is often used as an angle parameter. So if we have f and t, which are two continuous functions defined by the parameter t, then the equations x equals f of t and y equals g of t are called parametric equations. The collection of points x and y obtained as t varies is called a plane curve. Plane curve. So let's determine the Cartesian equation for the following parametric equations. So to start, we've got x equals t take 3 and y equals 2t squared. What we want to do here is rearrange the first equation to make t the subject. So to do that, we need to add 3 to both sides. So we get t is equal to x plus 3. We can then substitute t into equation 2. And we get that y equals 2 times x plus 3 squared, which means y equals 2x squared plus 12x plus 18. So that's going to be our Cartesian equation for part A. For part B, it's a little bit trickier. So to see what we need to do here, we need to understand what's going on with these two fractions. So if we were to try and look at these two fractions, we can notice that their denominators are the same. But if we just try to add those two, the numerator doesn't give us a lot to go with. It doesn't give us a factor of the denominator. What we actually have to do is square both components before adding it. So if we do that, we're still going to get a common denominator of 1 plus t squared squared, but now our numerator becomes 2t squared plus 1 take t squared squared. And the benefit of doing that is that 4t squared plus t to the 4. We're also going to get minus 2t squared, and we're going to get plus 1. When expanded and simplified, gives us t to the 4 plus 2t squared plus 1, which we'll notice is a perfect square and not just any perfect square. It is the same as the denominator. So we get 1 plus t squared squared over 1 plus t squared squared, which is equal to 1. So this is a circle of center, origin, and radius 1. So as we talked about before, the parameter can also be an angle theta. So we're looking at these 4 examples here, which have their parameter as an angle. Now, to do these, we need to use a lot of our angle identities. So looking at this first one, what can we do with cosine and sine to get rid of the angle? Well, if we add the squares, we can use the Pythagorean identity. So x squared, this is part A, x squared plus y squared is going to equal sine squared theta plus cosine squared theta, which is x squared plus y squared is equal to 1. For part B, similar idea that we need to do, but a little bit of extra movement we have to consider. So if we square this, we don't just get cosine squared, we actually get 9 cosine squared theta. So what we have to do is divide both sides by that 9. So we get that x squared over 9 equals cosine squared theta, and we get y squared equals 25 sine theta. So y squared on 25 equals sine squared theta. Therefore, when we add these, we're going to get that x squared on 9 plus y squared on 25 is equal to 1. All right. Part C, we're looking at x equals 2 secant theta and y equals 3 tan theta. So we have to use the property that secant squared theta subtract tan squared theta is equal to 1. So we need to square both of these terms again. That's going to give us x squared on 4 equals secant squared theta, and y squared on 9 equals tan squared theta. So if I then subtract x and y, so x squared over 4 subtract y squared over 9, that's going to give us secant squared theta subtract tan squared theta, which is equal to 1. Carrying on to part D, we have x equals sine theta, and we have y equals cosine 2 theta. So for this one, we have to take a different approach using the identity that this cosine 2 theta is equal to 1 minus 2 sine squared theta. So we know that cosine of 2 theta is just y, and we also know that sine of theta is x, so this is really just the same as saying y equals 1, take 2x squared. So as long as we know that identity, that's a pretty easy Cartesian equation to develop. All right, so let's take this idea of parametric equations and apply them to vectors. So a vector function r of t describes the position of a particle whose location varies according to a parameter t. That is defined by, let me just get it up. So that is defined by r of t is equal to, up here, r of t is equal to x of t I plus y of t j. what we want. Wait, what have I done? Oh, okay. So for the second part, consider the water slide example to our right. The path of the particle as a vector function is r of t is equal to ti plus negative 0.01 t, bracket t minus 10 cubed plus 7 j. So that's our vector function of that particle on the right. For each new value of t, a new position vector r is formed. So when t equals 1, if we substitute that in, we'll get that our point is 114, as seen on the right here. So that's our 114. Then we've also got 310, 5.8, 10.7, and 18.2, it seems. So each of those points comes from substituting in different values of t. Let's take a look at a slightly different example, because now I isn't just t, it's a function of t. So if we were to express the position of the particle as a Cartesian equation, we know that x equals 2 root t and y equals 5t take 2. So what we're going to do is rearrange this in terms of t. So we know that t equals x squared on 4. So we divide both sides by 2, we square it. We get that t equals x squared on 4. Therefore, y has to equal 5x squared on 4 take 2. For part B, we're asked to calculate the domain and range of the equation, then graph the path of the particle on a Cartesian plane. So for the domain, we know that t is greater than or equal to 0. It's given up in the question here. So what does that mean for our x? That means our x is also greater than or equal to 0. We also know for our range that t is greater than or equal to 0. So y is going to be greater than or equal to, this term here goes to 0, and all we're left with is negative 2. So our answer for that is y has to be greater than or equal to negative 2. So I'm going to do a pretty sloppy Cartesian plane drawing here, because I've been having issues with my stylus. It's going to go from negative 2, and then it's the function y equals 5x squared on 4 take 2. So it is a parabola. It's coming up like that. Okay, and it's going to have Cartesian equation y equals 5x squared on 4 take 2. And we're going to have x and y axes. And this point here, when y equals 0, is going to be 2 times 4 is 8 divided by 5. So that's going to be 8/5. All right, and that is the path of the particle on a Cartesian plane. We're then told in part C that at some point, the y component is equal to 8j. So we want to find the value of x. Well, we know that y equals 5t take 2, and we know that y is equal to 8 at this point in time. So t has to equal 2, because then this becomes 5 times 2, 10, take 2 is 8. So then if we want to find x, it's just going to be equal to 2 times root 2. Okay, and our last example, I believe, last example, the position of a bird is given by r of t is equal to 2ti plus 0.01 t cubed j plus 0.5 t squared k for t greater than or equal to 0 seconds. Determine the position of the bird at t equals 0 and t equals 15. So at t equals 0, r of t, so r of 0, is equal to, well, this is just 2 times 0. This is just 0.01 times 0 and 0.5 times 0. So this is actually 0i plus 0j plus 0k. And we have a fancy word for that, which is the origin. Okay, r of 15, if we substitute this into our calculator, we're going to get that the I component is 30, the j component is 33.75, and the k component is 112.5. Okay, so those are the positions. Now we're asked to find the straight line distance of the bird from the origin at t equals 15 seconds to 2 decimal places. So we're looking for the magnitude of the vector r at 15 seconds because we know it started at the origin. So the magnitude of that is going to give us the distance from the origin, which is going to be 30 squared plus 33.75 squared plus 112.5 squared. Altogether, if we compute that, that's going to be 121.22 meters from the origin. That is all for this video. Thank you very much.